In this video, you and I get to take a look at the logic, configuration, and verification of dynamic multi-point VPNs. Let's jump in. I'd like you to imagine that you and I have been called in by this company to make some recommendations of getting full connectivity between each of these sites. So here they have the headquarters site, here we have Site 2, Site 3, and Site 4 respectively. And we ask them, what is it you'd like to accomplish? And they say, well, basically we want full connectivity from any of our remote networks, for example, the 10.2.2 or the 10.4.4, and the headquarters local network of 10.1.1. We want full connectivity for any user to any of those remote networks. So for example, Bob here should be able to reach a server that's sitting on the 10.4.4 network. Now, one option that we could do if we had statically assigned addresses that were connected to the internet by all 4 locations, we could build GRE tunnels from site to site up to the headquarters location. So for example, interface tunnel 0 or tunnel 1 or tunnel 2, give it an IP address, specify the source of the tunnel, specify the destination of the tunnel. So in this example, R1 would have 3 tunnels, one to site 2, 3, and 4. And then adding a routing protocol on top of that, the 10.4.4 network could be advertised via the tunnel to R1. R1 could advertise that network to R2. And so Bob's traffic would go like this, over the internet to get to the 10.4.4 network and the server on that network. Now, GRE all by itself is not secure. So what we'd also do on top of that is we could use cryptography to encrypt any GRE traffic between these locations, and that would encrypt all that tunnel traffic. So now we have confidentiality and connectivity. And this, with just 4 locations, wouldn't take much to set up. And then comes the wrinkle. They say to us, well, do you mean to tell us that Bob's traffic has to go all the way over the internet to R1, and R1 has to reroute it all the way down to R4, and the reply traffic is going to take the opposite path going this way, all through the hub? And we say, yes, in this topology, that's how it would work. This is hub and spoke. Now, if they said, oh, that won't work, we want connectivity directly between R2 and R4, what we could do is say, well, we could build another tunnel. So we could build a tunnel between R2 and R4, and if we really do want a full mesh between R2 and R3 and R3 and R4. So now we have 6 tunnels. We're running routing protocols on those tunnels, including the 10 network space for all of the local networks, and we have full connectivity. Now, configuring 6 tunnels like that on 4 different routers isn't too painful, but if we add another location, for example, if this is R5, to do a full mesh, we'd have to build a tunnel from R5 to all other sites. So to do that, we'd have 4 more tunnels on R5's perspective and 1 more tunnel on each of the existing routers. And maintaining a full mesh, especially if there's new routers that are part of that full mesh, that is not manageable. The other thing that they tell us is that these IP addresses that we have on the Site 2, Site 3, and Site 4, they're not static. And so we say to them, what do you mean they're not static? They're here in your topology. They said, well, that's what they currently are, but they could change. R2, R3, and R4 are dynamically being assigned IP addresses, and they may change from month to month. And that alone takes the static tunnel scenario out of the picture, because we can't create a static tunnel to an IP address that may not be there the next day. Well, I guess we could create the tunnel, but it's not going to work unless that IP address is always that same IP address with a static tunnel. So our next option that we talk about is dynamic multi-point VPN, because with dynamic multi-point VPNs, we're still going to use GRE interfaces, but we're going to use a special type called MGRE, multi-point GRE. And with multi-point GRE, we'll create, for example, tunnel 0 on R1, and we'll create a tunnel 0 on R2, and tunnel 0 on R3, and tunnel 0 on R4. And the actual number of the tunnel interface doesn't really matter too much. But what does matter is that it's a multi-point GRE interface that we're creating on that router. Now, the interesting thing about a multi-point GRE interface is that we don't specify the details for both ends of the tunnel. So for example, we're not going to say tunnel source is this, tunnel destination is that. But what we are going to do is we're going to tell all these tunnel interfaces that they need to check in with the hub. And because that's part of the configuration, that also implies that the hub, we definitely do need a static IP address that's not going to change. Because if we tell all the spokes to report and check in with 15001, and then 2 days later, that's a different IP address, they won't be able to check in. And if they can't check in with R1, R1 doesn't have the ability to dynamically build a logical GRE connection back to that device. So from a tunnel perspective, with GRE running on those tunnel interfaces, our connectivity would look like this. And then we can use addresses for those GRE interfaces. For example, we might use 172.16.0.1 on R1, and .2 on R2, and .3 on R3, and .4 on R4. And the magic is when R3 checks in with R1, it's going to report in and say, okay, my tunnel address is 172.16.0.3 and my current interface address is 35.0.0.3. And that interface address is often referred to as the NBMA address, the non-broadcast multiple access address. And that's the one that R3 could have gotten through DHCP or point-to-point protocol over Ethernet, or whatever method the service provider is using to dynamically assign that IP address. So when R2 and R3 and R4 checks in, now R1 knows the whole picture. He knows the NBMA addresses of those spokes, and he also knows the GRE addresses, or rather the actual IP addresses on the GRE, the tunnel interfaces. So if we have Bob up here as a user on R2 who's trying to reach the 10.44 network, and maybe there's a server there he's trying to reach, the traffic would go through the tunnel up to R1, down to R4, R4 would deliver it, and the reply traffic would go back that same direction. Now here's the magic of how DMVPN and the protocol called NHRP really kick in. Through the routing protocol, R4 is advertising to R1 about the 10.44 network, and R1 is advertising up to R2 about this 10.44 network. And what R2 is going to believe is that the route to get to 10.4.4, it's going to think that the next hop is 172.16.0.4, this guy right here, and to get to that, the interface we're going to use is our GRE interface here on R2. So the first packet is going to go up to R1, and then R1 is going to reroute it down to R4 and be forwarded. However, R2, because it's going through that multi-point GRE interface, and because it's running something called Next Hop Resolution Protocol, R2 is going to make an NHRP request. And here's what goes on in the mind of R2. R2 says, I see the next hop. It's in my routing table of 172.16.0.4. If I knew the corresponding NBMA address, the non-broadcast multi-access address, aka the address that's connecting that router 4 to the internet, if I knew what that real address was, I could go ahead and send the packet directly to R4. I wouldn't have to go ahead and send it through the GRE tunnel through R1. I could build dynamically a GRE tunnel down to R4 and send it directly to him. So in this NHRP request, R2 is going to send that request up to what's called the NHS, the next hop server, which is part of the configuration for the tunnel interface on R2. And that request is going to say something like, I would love to know the NBMA address that's associated with this next hop of 172.16.0.4. And when R2 gets a reply back saying, oh, guess what? The NBMA address associated with this next hop of 172.16.0.4 is 45.0.0.4, then R2 can build a GRE tunnel directly to R4, and then future packets can go directly between R2 and R4 over GRE, as opposed to having to go through the hub. And DMVPN has gone through several iterations, and Phase 2 and Phase 3 of DMVPN are very similar. For example, R2, if it sees the next hop is out a multi-point GRE interface that's enabled with NHRP, it'll automatically kick off that NHRP request. With Phase 3, they had a little bit more control in the fact that if R2 tries to forward a packet through R1, there will be a specific NHRP redirect message saying, hey buddy, you might want to do an NHRP request to figure out the interface address, the NBMA address that's associated with that next hop. So with Phase 3, it's a little bit more aggressive. And also with Phase 3, it handles summaries better. So if we're dealing with summaries of network through the hub, we can manage those better with Phase 3. And also with Phase 3, due to some of the additional controls, it gives us better ability to manage hierarchical implementations of DMVPN, where we could have huge networks with multiple DMVPNs running with the potential for spokes from one hub to make a direct connection with spokes of a different hub. But regardless if we're using Phase 2 or Phase 3, the concept is all the spokes check in with the hub, all spokes can send NHRP requests to that hub, and then when the spokes resolve the NBMA address associated with that next hop in their routing table, they can then go ahead and take a shortcut, meaning we're going to go directly to that neighbor, to their NBMA address, using GRE, and not have to route future packets through the hub. Now what we've described right here is the magic behind DMVPN. And then on top of all that, whether it's Phase 2 or Phase 3, we're also going to put on IPsec, because we do want that data to be confidential as it's going through the network. However, one really important troubleshooting tip is that if DMVPN is not working correctly, we could temporarily take off the IPsec. And then without IPsec even involved, if we still have a problem where R2 isn't cutting over to R4, we could then troubleshoot that and narrow the fault domain down to what's really causing the problem, which in this case could be a misconfiguration of one of our spokes, or a misconfiguration of our hub, or a lack of connectivity between our spokes and our hub. And for this video, what we're going to do is we're going to do everything except for adding on the IPsec profile. And that way we can focus on the DMVPN component specifically. And then the next video, we'll take a look at just adding on top of that the IPsec protection with an IPsec profile. It's always a good practice to verify what we have in place before we start configuring additional parameters on a router. So here in R1 we have gig 1/0, which is 15.0.0.1. We have gig 2/0, which is the 10.1.1.1. And a loopback of 1.1.1.1, and we have no tunnel interfaces configured yet. But that's all about to change. So we're going to get into configuration mode and type in interface tunnel X. In our case, we're going to use tunnel 0. By default, on a tunnel interface, we're going to use GRE protocol, which is generic routing encapsulation. Now, on a traditional tunnel interface, we're going to have two parameters. We're going to specify the source of the tunnel, that would be on our local device, and the destination, which would be a tunnel interface on the destination. However, in our case, with DMVPN, we're not going to specify static tunnels. We're going to have multi-point tunnels. So here we've identified that the source address we're going to use for our end of this tunnel is going to be gig 1/0, which equates to 15.0.0.1. But instead of specifying a destination, like we would in a traditional static GRE tunnel, we're going to specify that we are going to use this as a multi-point GRE tunnel. And the syntax for that is tunnel mode GRE multi-point, which implies that some future time we could have this tunnel interface logically connect to R2 or R3 or R4, but it's going to take a little extra configuration on our tunnel interface at the headquarters site, as well as the tunnel interfaces at the branch or remote sites. As a security measure, we can specify a tunnel key, and that tunnel key has to match on any other incoming GRE traffic that wants to go ahead and become part of this GRE tunnel. So from a troubleshooting perspective, if we have R3 the spoke, and it has a tunnel key of 6784, and R1 has a tunnel key of 6783, that would definitely be a reason why the tunnel would fail to establish between R1 and R3. If everything else was configured correctly, but the tunnel key was wrong, that could cause it to fail. One of the key elements of making dynamic multi-point VPNs work is the NHRP, the Next Hop Resolution Protocol. So to configure that, we're going to configure those parameters also right here on the tunnel interface. So the first thing I'm going to add is the network ID. And the network IDs also have to match. So later when we're configuring R2, not only do we have to have the tunnel key correct, but we're also going to have the NHRP network ID correct. We also have a password that we're going to use for authentication purposes for NHRP. So right here on R1, we'll do IP, NHRP, authentication, and then our password. Of course, in a production environment, perhaps a password that's 8 or more characters, upper and lowercase, alphanumeric, special characters would be in order. For this demonstration, I'm going to use Cisco 123. And that would be yet another thing to check on the hub and spokes to make sure that the NHRP authentication key is correct. Now what's going to happen is R2 and R3 and R4 are all going to register with this hub. And it is going to dynamically learn their NBMA addresses, which are these guys circled in red, as well as their associated GRE tunnel addresses, which are going to be 172.16.0.r, with the R representing the actual router number. So to tell R1 on this tunnel interface that it's going to go ahead and learn those dynamically, due to R2, R3, and R4 registering, we're going to use the NHRP command of IP NHRP map multicast dynamic. And that says, okay, I'm willing to go ahead and learn those mappings dynamically. These next two commands of IP NHRP shortcut and IP NHRP redirect are the two big commands that make the difference between DMVPN Phase 2 and DMVPN Phase 3. So with the IP NHRP redirect command, if R2 sends a packet destined for 10.4.4 and it has the next hop of 172.16.0.4 and it uses R1 as its next hop, the IP NHRP redirect command simply tells R1, listen, if you get a packet that R2 has sent to you that you need to forward down to this next hop of 172.16.0.4, I want you to actively, says this command, I want you to actively send an NHRP redirect message up to R2 saying, hey, listen, buddy, there's a more direct path to that destination. If there really was a next hop address of 172.16.0.4, it's very likely that an NHRP request is going to be generated automatically because that next hop is off of that GRE interface. But as part of Phase 3 and the ability to have hierarchical DMVPN implementations, the IP NHRP redirect feature was added. So with these two commands added, effectively, we're running DMVPN Phase 3. And as part of that, when a request, an NHRP request is sent, so R2 has the next hop of 172.16.0.4, which is a GRE interface address of R4, and R2 is desperate to find out this NBMA address, so it can build the connection directly down to R4. As that request is sent up to the hub, what the hub is going to do, he's going to forward that request down to R4. And that NHRP reply, which has the information stating that the 172.16.0.4 has the NBMA address of 45004, the reply could go back the same path, or it could go directly back to R2. So although R1 has that information already because everybody registered, to allow some of the additional hierarchical implementations of DMVPN, that NHRP request is sent to the final destination, so that the reply back is straight from the horse's mouth. It's straight from R4. And check this out. If R4 already knows about the NBMA address of R2, which is 25.0.0.2 in this example, the reply back could go directly to R2, to its NBMA address. And again, cutting out the hub as a middleman for the traffic that goes between those two devices. Now on this tunnel interface that we're creating on R1, I'm going to give it the IP address of 172.16.0.1 on tunnel 0. And on R2, R3, and R4, we'll give it 172.16.0.2, 3, and 4 respectively, following the router number. So the syntax for an IP address on an interface is IP address 172.16.0.1 in this case, with a 24-bit mask. Now, one of the realities is that packets are going to get bigger and bigger as we add more stuff to them. For example, we're going to be adding a GRE header. We're going to be adding IPsec as we protect it. So we could tell this tunnel interface to go ahead and use path MTU discovery, which in theory is going to allow the devices on the tunnel to decide what the maximum MTU is, which in a perfect world would be great. And the reason that's helpful is that if we start off with a huge, for example, let's say we have a huge TCP segment, and it gets encapsulated in IP, and then we put it into GRE, and then we have IPsec on top of that. And the idea behind path MTU discovery is that we want to avoid fragmentation. So for example, if we start with a 1450 TCP segment of data, and then we're adding on a couple of IP headers with GRE and IPsec, it's possible we could be over what the media supports, and as a result, it would have to take that traffic and chop it up. And then we'd have fragments. So with path MTU discovery, maybe it says, okay, path MTU needs to be 1460. And then as we add on the GRE and the IPsec, perhaps that'll reach up to 1500, and at that point, it won't have to be fragmented, at least on Ethernet. So to enable tunnel path MTU discovery, you'd use the command tunnel path-MTU-discovery, and now we've enabled it. Now what I've also discovered, pun intended, is that this doesn't always work correctly, where we may have packets that are being dropped or fragmented because the MTU auto-discovery process didn't work correctly. And a lot of things could cause that. Part of MTU path discovery is ICMP traffic. So if ICMP is being denied in the path somewhere, maybe they couldn't correctly negotiate. So what I'd like to show you is another option. If we set the IP MTU to 1400, which is artificially low, then if we do add GRE and tunnel keys and IPsec, all of which are adding a little bit more and a little bit more, we're going to be safely under that limit of 1500. And to assist with that process, we might want to tell the transport layer protocol of TCP to go ahead and set its maximum segment size at 1360. And the syntax for that is IP TCP adjust-MSS space 1360. And the rule of thumb is whatever your IP MTU is, go ahead and set the TCP at the MTU minus 40 bytes. So if you set the MTU to 1420, the TCP MSS could be 1380. And in a production environment, what you're going to want to do is put these parameters in and then load it up with traffic and do some baselines. Okay, which works better? Which has better throughput? And put a protocol analyzer on the network to see what's really happening. And then in your network, when you find that sweet spot, go ahead and use that. But as a guideline, I like using these two as a starting point, and those will be fantastic, like for 95+% of the networks that we're going to see. And that's it for R1. We've configured a tunnel interface. We specified the source. We told it that it was a GRE multipoint. We specified a key. We put in the NHRP parameters, including the network ID, the key, the method that we're going to learn mappings, the two entries that cause this to be DMVPN phase 3, the actual IP address on that GRE interface, and the MTU related elements. Now what I'm also going to do, because I absolutely want you to lab this up and practice with it, I've also included this syntax of the lab that we're doing as part of the Nugget Lab files for this course. Next, let's go to R2 and configure it. Now, the tunnel interface on R2 is going to be slightly different, and that's because it's going to have a different GRE address. is going to have an IP address of 172.16.0.2. And what we're also going to do is we're also going to tell the tunnel interface about the NHS. That's the NHRP server's address. And that way R2, if it ever needs to send an NHRP request, it knows exactly who to send it to. And as part of that configuration, R2 needs to know two things. It needs to know the NBMA address, which is 15001. That's the interface that's connected to the internet. And R2's tunnel interface is also going to need to know the GRE address that's associated with the tunnel interface on R1, which on R1 is 172.16.0.1. So we're going to statically supply all of that information on R2's tunnel interface. So we'll make sure we go to the right router, which is R2. And in R2, we'll go into configuration mode. We'll create interface tunnel 0. We'll specify the mode is GRE multipoint. The tunnel source is gig 1/0. And the tunnel key has to match exactly what the key was over on R1. And that key was 6783 for the tunnel. So up to this point, the tunnel interface configuration looks a lot like it did on the hub. And some of our NHRP commands are the same too. IP NHRP network ID 1 matching the hub. IP NHRP authentication Cisco 123 matching the hub. The command for IP NHRP shortcut matches what we did up on the hub. But here's where we start to change a little bit. On R2, we're going to specify what the NHS is. Now, NHS is an acronym for the NHRP server. So we're going to say IP, NHRP, NHS, and we're going to give it the GRE IP address of the server. In this case, R1, which is 172.16.0.1. So with this command, R2 now knows the GRE address, 172.16.0.1, that it can use to forward NHRP requests to. However, the real problem is that R2 doesn't know what the NBMA address is, the interface address that's connected to the internet to reach 172.16.0.1. So we're going to add a static mapping that tells R2, listen, to get to this address of 172.16.0.1, the associated NBMA address is 15.0.0.1. And the syntax for that is IP NHRP map, and we're going to put in the GRE IP address followed by the interface IP address. So as far as syntax goes, if you're ever curious, okay, which one of those goes first again? I want you to think of A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. And the reality is that G comes before I, meaning we're going to put the GRE IP address before the interface IP address. We're also going to tell this interface that from an NHRP perspective, anything related to broadcast or multicast, we should also send it up to the IP address of the hub, which is 15.0.0.1. So the syntax for that is IP NHRP map multicast and then the NBMA address of the interface of the hub. Next, we need to give the actual interface on R2, the tunnel interface, an IP address. So we use the syntax IP address 172.16.0.2 with a 24-bit mask. And let's also specify the MTU and also the TCP adjust maximum segment size of 1360. And that'll help avoid fragmentation of packets as they're going through that interface. Now the syntax on R3 is going to be virtually identical, except we're going to change the GRE interface IP address to 172.16.0.3 instead of .2. So we'll do this one a little bit faster. So we'll go into configuration mode, interface tunnel 0, tunnel mode GRE multipoint, tunnel source gig 1/0, that's the internet facing interface, and tunnel key 6783 because that's what everybody else is using for their keys. And that key is going to need to match on all of our devices for multiple reasons. Number one, if we want to have that tunnel with the hub, it needs to match the hub. And if we're going to dynamically build shortcut tunnels between R2 and R4 or between R2 and R3, if that key doesn't match, we won't be able to form those tunnels. For NHRP, we're going to say the network ID is 1 and the authentication is our password of Cisco 123. We're going to specify the next hop server is at 172.16.0.1. That's the GRE interface address of R1. We're going to do the mapping just like we did on R2 that says, okay, this GRE address maps to this NBMA interface address. And we have the multicast and shortcut NHRP commands just like we set up on R2. And then, of course, we need an IP address. We're going to do 172.16.0.3 with the 24-bit mask. And we'll do the IP MTU adjustment and the maximum segment size controls here on R3 as well. And on R4, our last one, let's do this as well. We're going to go into configuration mode, interface tunnel 0. It is GRE multipoint. Our tunnel source is the interface facing the internet, and the key is 6783. Again, those parameters have to match if we want it all to work correctly. We'll supply our NHRP information, the network ID, just like we did before on R2 and R3, the authentication key, the next hop server's address, the mapping for that next hop server with the GRE interface address of that server followed by the NBMA interface address, the multicast and the shortcut commands as well we're going to apply on these spokes. Now, one of the big differences is that we aren't using the IP NHRP redirect command on the spokes. The redirect command is just for the server, but the NHRP shortcut for DMVPN Phase 3 is going to be used on all the branches as well. Let's specify the IP address for this interface, which is going to be .4, and the IP MTU of 1400, and the TCP adjust maximum segment size to 1360, just like we did on all 3 other routers. Now, what should have happened is R2, R3, and R4 should have all registered with the NHS, which is the acronym for the NHRP server, or next hop server. And each of these routers, as they register, would provide the GRE address assigned to their GRE interfaces, as well as their interface addresses, the NBMA addresses. So it's important to verify that that actually works. Let's make a road trip over to R1, and on R1, let's do a show IP NHRP, and that will show us all the mappings that are currently in place. And from this output, here's what R1 thinks. R1 says, okay, great. I know that this device at 172.16.0.2, which is the tunnel interface of R2, has the address 172.16.0.2 and the physical interface connected to the internet, which is the NBMA address, the non-broadcast multi-access address, associated with that IP address is 25.0.0.2. And it has similar information for R3 and R3's NBMA address, as well as R4 and R4's NBMA address. So again, the tunnel interfaces are 172.16.0.R with R being the router number, 1, 2, 3, 4 respectively. Now the next trick is how do we get these networks 10.4.4, 10.3.3, 10.2.2, how do we get them advertised over to R1? And the answer is we're going to use a routing protocol, and there's lots of options. We could use things like RIP or EIGRP or OSPF. Heck, we could even use BGP or ODR if we wanted to. So for our example, let's use EIGRP. Let's use the autonomous system number of 777. And let's include the network 10, because that'll include all of these remote networks. And let's also include 172.16, because that will include all of our tunnel interfaces. So to configure that on R1, let's go into configuration mode. We'll go into router EIGRP 777. We'll do a no auto summary, even though that's a default in iOS 15 and higher. And let's put in networks 10 and network 172.16, and we're set. Now, one of our other challenges, and this applies to DMVPN Phase 2 and Phase 3, is that if we're using EIGRP, there's a thing called split horizon, which is a distance vector characteristic, and it simply says this: if R2 is advertising the network 10.2.2 down to R1, and R1 learns it on tunnel 0, split horizon says if you learned it on tunnel 0, don't advertise it back out on tunnel 0, which means if we don't advertise it back out, it means that R4 won't get the update. It also means that R3 won't get the update. So we need to disable split horizon for EIGRP 777 on this tunnel interface if we want the other spokes to learn about R2's networks. And vice versa. If we want R2 to learn about R4's networks and R2 to learn about R3's networks, we need to disable split horizon for EIGRP on the tunnel interface on the hub. Another challenge that we're going to have with EIGRP is that if all of our tunnel interfaces are all on the 172.16 network, when R4 advertises the 10.4.4 network, and because split horizon has been disabled, or we will disable it on R1, that route gets advertised up to R2, we don't want R1 to put his IP address, which is 172.16.0.1, as the next hop. Instead, we want the 172.16.0.4, which is the GRE tunnel interface on R4, to be shown as the next hop to R2. Because that's what triggers R2 to do an NHRP request to find out the NBMA address associated with 172.16.0.4. So in the case of EIGRP, we're also going to want to disable next hop self, that feature for EIGRP 777, on R1's tunnel interface, just to make sure that the correct next hop, which is R4's tunnel interface, is carried up in the routing updates up to R2. So to do that, we'll go into interface tunnel 0. We'll do a no IP next hop self for EIGRP 777. We'll also turn off split horizon on that interface for EIGRP 777. So if we do a show IP protocols, we should be able to see that EIGRP is running. However, we haven't learned anything from any neighbors yet because we have not yet configured R2, R3, and R4 for EIGRP. So let's make a road trip over to R2, And on R2, we'll do router EIGRP 777, no auto summary, just for good measure. We'll add network 10 and network 172.16. And now we should have a neighborship that pops up almost immediately with EIGRP between R2 and R1. And that's fantastic. We have a neighborship. We'd want to do that exact same configuration over on R3. So we'll go into configuration mode, router EIGRP 777, no auto summary, network 10, network 172.16, and that also should bring up a neighborship between R3 and R1. And then we have to do R4 as well. It's the exact same syntax. Router EIGRP 777, no auto summary, network 10, and network 172.16. So the 10 networks are all the networks that are directly connected to our branch and our headquarter routers, and the 172.16 represents the GRE tunnel interfaces on each of the routers. So to verify everything's in order, let's go back to R1, and it shows 3 adjacencies have come up. Let's do a quick check with show IP EIGRP neighbor right here on R1, and we have 3 very happy neighbors. If we want to verify the routes that we've learned via EIGRP, we can do a show IP route EIGRP. And there's the 10.2.2 network that we've learned from R2, the 10.3.3 network that we learned from R3, and the 10.4.4 network that we learned from R4. And if we made a road trip over to R2, we would expect to see the 10.1.1 network, the 10.4.4, and the 10.3.3 all as dynamically learned routes. So let's check that out. Let's go over to R2 for a moment. And on R2, we'll do a show IP route EIGRP. And sure enough, we have the 10 networks respectively from the other 3 routers. So in R2, let's pick out one of these routes. In fact, let's pick the 10.4.4 network, which is being advertised from R4. It's being advertised up the tunnel to R1, who's advertising it back to R2. It's not using next hop self. So we have the GRE IP address, the tunnel interface on R4 as the next hop. To confirm that, we could do a show IP route for 10.4.4.4 explicitly. So show IP route for 10.4.4.4 says, yep, I've got a route for the 10.4.4.0/24 network. The next hop is 172.16.0.4, which is the GRE interface of R4. And I learned this update from 172.16.0.1, which is the GRE interface of R1. Now here's where the magic of NHRP comes in as part of DMVPN. If the user Bob or someone else sent a packet to 10.4.4.4, R2 would say this needs to be routed out my Tunnel 0 interface, which is a multi-point GRE interface configured with NHRP. And R2 would say, do I know what the NBMA address is associated with 172.16.0.4? And it will look inside of its cache to see if there's a mapping already present. And if there isn't a mapping already present, what R2 is going to do is send a packet to R1 over the GRE tunnel saying, hey, I've got a packet destined for 10.4.4.4. Because you're my next hop server, I'm going to send it to you, and hopefully you'll know how to get there. So this is the packet being sent. Now, in addition to the packet being sent, there's also going to be an NHRP request going to the server saying, hey, I would like to know what the MBMA address is associated with 172.16.0.4. So I'm going to put that request in green. So that request goes to R1. And with DMVPN Phase 3, the actual request is forwarded down to R4, who owns that address, because R1 knows the mappings. And R1 replies with the information about the mapping between itself at 172.16.0.4 and its NBMA address of 45.0.0.4. So now, armed with that information, what R2 can do for his subsequent packets, instead of sending them through the tunnel to R1 and have R1 forward them down to R4, the actual packets can be sent through a new GRE tunnel that is dynamically established between R2 and R4. Because R2 now knows the NBMA address, the reachable IP address on the internet for that remote spoke. And replies also can go back. So that's our spoke-to-spoke connectivity that can be dynamically set up and established, primarily because of the NHRP mechanism that's in place. Now in addition, when R4 gets that NHRP request, and it sees that it came from 172.16.0.2, if it already has the mapping and knows the NBMA address for R2, it can reply directly back to R2. It doesn't have to reply back through the hub. So we can think of the hub just as a starting point for building the infrastructure. And then once the communications get going, the spokes can communicate directly with each other. Now up to this point, it's all just GRE traffic, which is not protected. And that's why on top of all this, we simply add on IPsec, which is a fairly easy thing to do, that provides the confidentiality of our DMVPN. So in my opinion, DMVPN is still DMVPN even if we don't add IPsec for confidentiality. because we're dynamically setting up virtual private networks on the fly between our spokes. And adding on the IPsec simply adds confidentiality to our DMVPN. So still looking here at the console of R2, let's do a show IP NHRP summary. And at this point, R2 says, well, I have one static mapping, that's for the NHRP server, and I have 0 dynamic mappings. I don't know where anybody else is as far as their GRE address to their NBMA address. All I know is about the NHS. If we want to see the details about what it knows, we'll do a show IP NHRP, and that'll reveal the details. And from R2's perspective, it says, yep, I know that the GRE address of 172.16.0.1 maps to the physical or interface address of 15.0.0.1, and I know that because it was statically configured in the configuration of my own tunnel interface. Now let's do some magic. Let's do a debug of NHRP. Now with that on, let's generate a ping request and send it down from R2 down to 10.4.4, and the interface address on R4 is .4. So what will happen is the initial traffic will go through the hub, but there will also be NHRP requests and replies so that subsequent packets can go directly down to R4. And in the background, R4 is also going to do NHRP requests to find out R2's NBMA address that's associated with the next hop of 172.16.0.2, which leads up to 10.2.2. And then all the future traffic between those two networks can go directly between those two devices and not have to go through the hub. So we're going to do a ping request. I'm going to do a Sean Connery on Hunt for Red October. One ping only. Let's do a ping to 10.4.4.4, repeat 1, and let's say source is gig 2/0, which is going to be sourced from the 10.2.2 subnet. And now that we have that debugged, let me go ahead and turn off debugging, and let's look at the output that it just generated. Now because R2 knew that the next hop was 172.16.0.4 from the routing table, and that the egress interface was its tunnel interface, and it also knew that it didn't have a direct mapping for 172.16.0.4, it sent the packet to the next hop server at 172.16.0.1 and said, buddy, you're on this network, you're the next hop server, hope you can help us. Please route this for me. However, R2 didn't stop there. R2 also said, you know what? I've got this NHRP configured. I need to find out for myself from the NHRP server what the NBMA address is for the device that owns 172.16.0.4. And that's what we have right here. We have an NHRP resolution request for destination 172.16.0.4. And the reason R2 wants to learn that, it doesn't want to have to send all of its packets through the hub to get to that destination of 10.4.4. It says if I can learn the NBMA address, which is 45.0.0.4, associated with that next hop, I can build a GRE tunnel dynamically to R4 and send packets directly to R4 on that new connection. So here's the actual request. I need to find out about the NBMA mapping for that host. I'm sending the request at 172.16.0.1, and over here it says I'm using a source of 172.16.0.2. So if we scroll down a little bit, we have the continuation of the story. We have NHRP successfully resolved 172.16.0.4 to the NBMA, that's the interface address, of 45.0.0.4. So behind the scenes, when R2 sent that request to R1, R1 actually sent the request onto R4. R4 replied back, possibly through the hub, or possibly directly to R2 if the resolution had already been done, meaning that R4 knew that to get back to 172.16.0.2, that the NBMA address of R2 was 25.0.0.2, that reply could have gone directly back to R2. Now the end result is that R2 and R4 know directly how to connect to each other thanks to NHRP, and they don't have to send traffic through the hub. So if we use the up arrow key a few times and did a show IP NHRP again, now R2 still knows about the static mapping for R1 and its interface address. It knows about itself, which is kind of funny. And the flag router indicates that it's a routing device itself that has devices behind it it's doing routing for. It's not an end device. And the unique flag simply says, if there's an NHRP information that comes in that's different, don't believe it. Effectively, we're not going to override this mapping, because it's our mapping, with a different IP address or a different NBMA address, which could possibly happen if we had another spoke, for example, that was misconfigured with the same tunnel IP address as R2. And if that happened, where we configured 172.16.0.2 on R3's tunnel interface, and R3 registered and that information was advertised, then we have another mapping that says 172.16.0.2 is mapped to the NBMA address of 35.0.0.3. But the unique flag says, don't let another mapping that comes in override this information right here. And there are options to turn off that behavior, so you can have them overwritten if you want to. And most importantly, for our discussion, 172.16.0.4 that we have as a next hop to get to the 10.4.4 network, this NHRP information now shows that the NBMA address, the reachable address on the interface connected to the internet, is 45.0.0.4. So for future packets that need to be sent, R1 is not going to send them through the hub. If they need to go to 10.4.4, R2 can just use that multi-point GRE interface and build its own connection directly to that IP address of 45.0.0.4 and send traffic directly to R4 instead of going through the hub. Now if we do the up arrow key a couple times and do a ping again, and the up arrow key a couple more times and do a show IP NHRP again, I want you to notice something that changed. We have this additional flag that says used. So there's like a 2-minute counter. If traffic has been sent using this mapping in the last 2 minutes, we're going to see this flag of used to indicate that we've recently used that NBMA address, which is associated with that next hop, to forward traffic directly to R4. If we want to clear the mappings, we can do a clear IP NHRP and then put in the mapping that you want to go ahead and remove. A few up arrow keys, we'll do a show IP NHRP. You notice that the mapping for 172.16.0.4 is gone. I thought it would also be fun to take a look at a protocol analyzer of a request and a response with NHRP. So here in packet 17, we've got this NHRP request. And in that request, R2 is saying my source NBMA address, the IP address on my interface, is 25.0.0.2. My source protocol address, which is the IP address on my tunnel interface, is 172.16.0.2. And the destination protocol address, the GRE address that I'm looking for to resolve, is 172.16.0.4. So if we take a look at the outside IP header, it's coming from 25.0.0.2, that's R2, going to 15.0.0.1, that is R1. But take a look at this reply, the next packet, in packet number 18. So in this response, check out the layer 3 header. It's coming from 45.0.0.4. That's the NBMA address of R4's interface connected to the internet. And it's destined to our NBMA address, or R2's NBMA address. So this reply is coming straight back to R2, not going through the hub. It specifies that this is a reply. Here's the initial information that was in the request. And as far as the answer goes, the client's NBMA address you're looking for, which is mine, says R4, is 45.0.0.4. And my tunnel interface address, the protocol address, is 172.16.0.4, which is the whole reason we started asking in the first place. We wanted this mapping so that R2 could start talking directly to R4. And if you want to take a look at these two, I just exported just these two packets in a separate file called nhrp.pcapng. And I've included this packet capture in the Nugget Lab files associated with this course. And if you're interested in learning more about Wireshark specifically, you may want to check out our Wireshark course here at CBT Nuggets. Your homework assignment for this video is to lab it up. Inside of the Nugget Lab files, in addition to the packet capture that we just looked at, I've also included all of the commands that I've just implemented on R1, R2, R3, and R4, and I would strongly encourage you to practice in setting up DMVPN and also using the commands to verify that it's working. Because once we have the basic components of DMVPN working, our next step is to add on top of it IPsec, which adds the confidentiality aspect using encryption to protect our IP packets as those GRE tunnels are forwarding traffic between the headquarters and other sites. So again, step 1, lab it up, and secondly, once you have it labbed up, in our next video, we'll take a look at IPsec. Meanwhile, I hope this has been informative for you, and I'd like to thank you for viewing.